Welcome to this video. In this video we will introduce the op-amp, what they are, what they do, and how to analyze circuits that include op-amps. Op-amps are extremely useful devices. Op-amp is actually short for operational amplifier, and if you want to be a cool engineer you say op-amp. An op-amp is a differential, high input impedance, high gain, low output impedance device. And it's used typically in feedback configurations to implement all kinds of useful circuits. You can build amplifiers, you can build filters, you can convert currents to voltages, that is, take a voltage signal and come up with a current signal that's related to the voltage signal. You can buffer between two circuits. It's really a versatile device. It's extremely helpful. So what we have on the screen is the op-amp symbol. This shows everything that you might want to think of connecting to an op-amp in a circuit. We'll start with the supplies. The high supply and the low supply are basically the power supplies to the op-amps. And the high supply you typically connect to a voltage source somewhere between 15 and 5 volts, depending on the op-amp. Excuse me. The low supply you connect to typically negative 15 to negative 5, although it's becoming more and more prevalent to have op-amps where the low supply is 0 and the high supply is, say, 5 volts. The supply voltages we typically won't talk about when we're doing circuit analysis because they're the sorts of things that you can ignore unless you're in a situation where you can't. And what I mean by that is you typically don't need to worry about the supply voltages unless your output is getting close to one of the supply voltages. Because of the way things work, your output will never go above the high supply or below the low supply. And so they form limits on the magnitude of your output. And depending on the type of op-amp, your output may not be able to get closer than about 1 volt to either supply. There are devices called rail-to-rail op-amps where the output can get to within a tenth or even less of a volt of the supplies. So those are the supplies. Again, you have to connect them up to make a real op-amp work, but we're not going to worry about them much. We have two inputs. We have a non-inverting input and an inverting input. And these two inputs are typically connected to other bits of circuitry. And the op-amp takes the difference between the non-inverting input and the inverting input, multiplies it by a gain. We typically write the op-amp gain as a capital A, and that becomes the output of the op-amp. So again, the output of the op-amp is the gain times the non-inverting voltage minus the inverting voltage. Now, op-amps typically have what we call very high input impedance. So the current going into each of these nodes or out of each of these nodes is very low. The gains are usually pretty big, typically somewhere between about 1,000 and 100,000. The output, there is an internal resistance, which is typically very low. Okay, so because the gain is so large, and the gain typically is somewhat variable, it's not two op-amps may have a gain A that differs by as much as a factor of 2 or even more. So you can't rely on the gain to be exactly what you want, and because the gain is so large, you typically employ an op-amp in a feedback configuration, and we'll talk about that in just a minute. A more detailed model of an op-amp is the following. The plus sign, this guy here is the non-inverting input. This is the inverting input. They're connected together by a resistor, and the resistor is called the input resistance. Again, typically this input resistance is pretty big. You can also think of the op-amp as having a voltage-controlled voltage source, where the output of that voltage source is the gain times the difference between the inputs. And then there's an output resistance, which is typically fairly small. For a typical op-amp, it may be as low as a couple ohms. Usually it's not more than about 50 ohms, depending on the application. Okay, so that brings up the question then, how do we do the analysis? And it turns out that this model that we have here is sometimes called the detailed model, which is a misnomer because this is actually a very simple model if you look at what actually is involved in putting together an op-amp. Inside a real op-amp circuit, there are somewhere between 20 and 40 transistors and a lot of resistors, and a whole lot of effort has gone into the design. So this is a much simpler model than the actual circuit, but this again is what we call a detailed model because it shows the input resistance, the output resistance, and the gain. Now again, as I said, in real life, in many applications, we don't have to worry about this detailed of a model. We can use what we call the ideal op-amp model. And the idea behind the ideal op-amp model is the input resistance is infinite, so it's like the two inputs just go to terminals inside the op-amp, and the output resistance is 0, so there's no output resistance, and the gain is infinite. Okay, so this might lead you to believe that this is a dumb thing to do. If I make the gain infinite, then if the difference between the inputs is anything but 0, then the output's going to be infinite. And we don't want that. We can't use that in real life. But the idea is that these three conditions, and particularly making the gain infinite, can be interpreted as the source output will be whatever it needs to be in order to make the voltage at the non-inverting input, this guy, equal to the voltage at the inverting input. And so you may think that this is not an obvious thing, and it actually is a concept that tends to be a little difficult to get straight, but once you do, it makes analysis of op-amp circuits actually much easier than they otherwise would be. So again, this is our ideal model. This is how we model the op-amp when we don't have to worry about input resistance, and we can assume that the output resistance is 0. This is a pretty good model for most things, at least as a first pass. Okay, so that's an introduction to the op-amp. We've covered a lot of concepts, but let's actually see if we can now apply what we know about the op-amp to a particular op-amp circuit and see what it does. This op-amp circuit is called a voltage follower. And you can see that the output of the op-amp is connected back to the inverting input. And the non-inverting input is connected through a 300 ohm resistor to a 3 volt source. You'll notice that I've got the op-amp connection to ground, basically so that I know that my op-amp knows what ground is. You'll notice that I don't have the high supply and the low supply lines drawn on this. And the reason for that is, again, we ignore those supply lines when we're doing this analysis. It might not be a bad idea after we're done with the analysis to see whether or not the output will ever get above the high supply or below the low supply, because if it does, then we're in trouble, because in real life the op-amp can't do that. So let's see how we might analyze this. First, we'll use the realistic model, it's sometimes also called the non-ideal model, where we have an input resistance. And in order to show you how this stuff works, I'm going to make the input resistance fairly small relative to what it would actually be. I'm going to have it just be 1 k ohm. And then we have also inside the realistic or non-ideal model a voltage source connected to an output resistance, and let's set the output resistance to 50 ohms. And let's set the gain on the voltage source to be 10. So for this case, we'll say that the output is 10 times the voltage at the non-inverting node minus the voltage at the inverting node. Both of these voltages, by the way, are referenced with respect to this ground node. Okay, so again, this is what you would call a really crummy op-amp. In real life, the gains here the gain is much larger and the input resistance is much larger. But the reason for doing this is that it will hopefully show you how the op-amp works, how feedback is involved, and so on. So now, in principle at least, we have enough information to solve the circuit. But to make sure it's clear, I'm first going to label this term. The voltage across this 1 k ohm resistor is, in fact, V plus minus V minus. Okay? It's the voltage at the non-inverting input here minus the voltage at the inverting input. So in order to make the analysis seem clearer, though, let's redraw the circuit as follows. We'll keep our 3 volt source. We still have the 300 ohm resistor. And now we'll draw the 1 k ohm internal resistance. This is still 300 ohms. And this will get connected at some point to the output of our voltage source, our dependent source. So this is 50 ohms, and this is 1 k ohms. Okay, so hopefully, and then let's see, we have plus or minus. This is again V plus minus V minus. And this is going to be 10 times V plus minus V minus. So if you feel the need at this point, you might pause the video to make sure that I've actually drawn this correctly. Well, I forgot the 1 k ohm. And the thing we're actually interested in here would be the output voltage of the op-amp. Okay. So let's see where to go from here. We're actually close enough to the end of this video that I think I'll stop here, and at the beginning of part 2 we'll do the analysis of the voltage follower using this realistic or non-ideal model, and then we'll redo the analysis of the voltage follower using the ideal model, and you'll hopefully begin to see how the ideal model makes your life easier. Okay, but for now we'll stop. Join us in part 2 of this video.